Welcome to another MathCast. In this episode, we're going to be taking a look at integrating factors again, although this time we have an initial value problem. So it'll be all the more important to force the integration constant into the problem at the end of the process. Let's first make sure we have it in the correct form. Looking at it, it's already in what we would call standard form. And so we want to start out here by listing the relevant pieces. Our P of t for this problem is minus n over t, which means that our integrating factor here, u, is e to the integral of minus n over t dt. Having an n here instead of a number makes this a little bit more complicated to work through, but remember the integral is with respect to t here. So it shouldn't cause you too much problem. This is the same thing as e to the minus n, and this will end up being a natural log of absolute value of t, which is the same thing as absolute value of t raised to the negative n. Now, remember that this is dependent on whether n is even or odd. You might want to deal with the positives or negatives here, but remember we only need one integrating factor, so it doesn't matter if this is positive t or negative t for our purposes here, both will work. And so I'm just going to keep this as t to the negative n, and that's what we're going to end up multiplying through by. So if we take the original equation and multiply through by the integrating factor, we get t to the negative n times x prime minus t to the negative n times n over t times x, and then I get e to the t times t to the n, and luckily that looks like that's going to cancel out wonderfully there. So let's clean this up just a little bit. This is t to the negative n times x prime, and you need to be careful on this one. You've got a t to the negative n and you've got a t. Remember what happens there is because that t is in the bottom, you're going to subtract those exponents. So this is going to be minus n times t to the minus n minus 1. Got to be very careful with the exponents on that one. Here, these two guys are going to cancel out, so I'm just going to have an e to the t. All right, so looking at this does not appear to be too bad. Assuming everything went correctly, which it looks like it did, I can pull this back on the left-hand side, kind of reverse product rule. And so cleans up pretty nicely. If I then take the integral of both sides, I'm looking at e to the t dt. And once again, taking the integral and forcing this integration constant now back into the problem, since this is an indefinite integral. I would have x is equal to t to the n e to the t plus c times t to the n. Now, I want to apply my initial condition x of 0 equals 1. And so if I'm looking at this, x of 0 equals 1 would imply that 1 is equal to, I'm letting t be 0 here. So I get 0 times 1 plus, let's see here, if t is 0, I get 0. So t equal to 0 looks like it's a bad point. Why might that be? Notice I can't solve for, I get 1 equal to 0 in this case. So something went wrong. What is it? Well, it's this initial condition. If you look at our original problem, we have n over t, and yet I want to know the value of this differential equation when t is 0. But notice if t is 0, I'm in for tough sledding because the differential equation itself becomes undefined. This can often happen with differential equations, and when it does, it's something called a singularity. So this is a singular point of the differential equation t equal to 0. So this is not going to be a good initial condition. Basically, this means there is no solution that passes through the point 0, 1. So just for the sake of coming up with a good answer here, why don't we change up the problem a little bit And instead, I'm going to look at, say, x of 1 equal to 1. So with this new initial condition, I've got 1 equals 1 to the n, e to the 1, plus c times 1 to the n. So cleaning this up a little bit, it looks like in this case that c is going to be 1 minus e. And so our particular solution, remember, since we're solving an IVP, it's not a general solution anymore. We've identified the one solution that passes through the point 1, 1 in this case. So our particular solution is x of t equals t to the n, e to the t, plus, replace c with the value 1 minus e, t to the n. And so this is the particular solution for this IVP. So this is another example of integrating factor method, only this time we've applied it to an initial condition. And we've also talked a little bit here, our first sort of glimpse of what are called singularities. We'll talk more about singular differential equations a little bit later in the semester, especially when we get to second order differential equations and start talking about things like existence and uniqueness. I hope this gives you a little bit more insight in how to apply integrating factor method. And in the episodes coming up, we're going to be taking a look at some models that depend on linear equations, and so it's good to get this out of the way now. All right, thank you for watching.